All right, so today we're going to start a new model, Bernoulli's equation. I'm sure you guys have heard of this before. We're going to derive the Bernoulli's equation today, and our goal with the Bernoulli's equation is to get a model that we can use to predict the behavior of fluid in such a way that given some pressures, velocities, and heights, we can calculate other pressure, velocities, and heights. And one of the important things we're going to hammer today over and over again is that this is for some very specific circumstances, which is why we're going to go through the derivation today. Then those specific circumstances are important. First, though, some vocab. So, streamline. A streamline is a line or path that is tangent to the velocity everywhere in the flow. So this is going to look almost exactly like you would expect it to. Anytime you see a computational fluid dynamics simulation and they show the path of the fluid, they'll show a streamline almost universally, unless they're showing a path line or a streak line. And we'll talk about those later when we start going into some stuff with chapter 4. But for now, I just want you to know that a streamline is the path that is tangent to the flow everywhere. So let's talk about two different types of flow. We have steady and unsteady flow. So steady flow is the same at all time, which means it's not turbulent, by the way. But if we were to draw a streamline like this, we know the fluid's expanding as it comes out of here, so it's going to come up. The fluid's going to come out and go wider. And I want you to draw two more streamlines in this nozzle. This is a nozzle here. Draw three more streamlines. Space them out. Go ahead, stop the video. All right, let's keep going. So if we draw another one closer to the edge, it's going to go more. One right in the middle, since it's a symmetric nozzle, is going to not deviate at all. So this is steady flow. Now, it's a steady flow. So our streamlines always look the same, right? Unsteady flow looks a bit different. So if we have a blunt object in our flow and our flow is fast enough, and we're going to talk about what that means when we get to Reynolds number. If it's fast enough, our inertial effects are going to become very important, and our flow is going to start becoming somewhat chaotic, and then it's going to become unsteady for flow. So I'm going to draw two streamlines. What I'm going to draw is way up here at the top. I'm going to draw an easy one like this, and then I'm going to draw one here, and I'm sure most of you guys have drawn your hand through some body of water, either be it a bath or a stream or a lake, and you can watch the water swirl and tumble behind your hand, and that's exactly what's going to happen here. So fluid is going to come along, it's going to meet this obstruction, it's going to meet other fluid, and it's all going to pile up, so it's going to come up around it, and it's going to try to make this bend, but it's unable to, right? Water is just like your car. It cannot make a 90-degree bend if it's going fast enough. And so it misses, and a low pressure region here develops, but the water tumbles around and starts producing these vortices and makes rotational flow. You can actually see it rotate, right? Which is why it's called rotational flow. So that's an instantaneous, let's say, streamline there. Now I want you guys to draw a bunch more streamlines in here, and you can guess that they're going to transition smoothly between something really chaotic like this one on the bottom and something nice and straight on the top. So go ahead, pause the video, and draw some streamlines. All right, I'm going to draw some now. So we're going to start to get a little bit of a bend like this. And then we're eventually going to get entrained in this flow, and the closer we get to the obstruction, the more unsteady and the more turbulent the flow is going to get, the more rotational the flow is going to get. So it's what's important to know is that with steady flow, if you release a particle in the flow, released in the flow from the same position, take the same path. With unsteady flow, that's not true. So you can imagine if we release a tiny particle here, and then we wait some time, and then we release another tiny particle, same spot. One of them is going to because these streamlines are changing with time, right? These particles will always follow a streamline, but the streamlines are changing with time, so their paths are going to change with time. So the particles are going to have completely different paths, and their paths are going to diverge more and more the farther in time you go. So with unsteady flow, this is obviously not true, and also, like I said, we should also note that the flow is rotational. Is rotational because it's rotating, right? And just a point of clarification here. You probably have heard the term laminar flow. Well, then if we go in increasingly chaotic, we go to rotational flow, and really all turbulent flow is also rotational flow, but we'll talk about some examples where we'll have rotational flow that's not really chaotic. It's actually quite well ordered. Got nice shedding vortices like Kármán vortex street, things like that. But rotational flow, and then eventually it becomes turbulent, where we have this chaotic, unsteady flow. So with all this vocab now out of the way, let's return to our goal, which is to apply F equals ma in a way that makes sense for flow. When the hard part about this is if we look back at this nozzle, and by the way, we're going to try to focus right now just on this kind of flow. For just a moment. If we look at this, right, the direction of motion for fluids changes all of the time, right? All of the time. So we really have to be careful about how we apply F equals ma, because when we did it with fluid statics, I don't know if you noticed, we always would say some of the forces in the y direction, and that's it. And that simplified our equations immensely. And we don't have that luxury here. We don't have that luxury. So let's look for a moment, though, at flow around a sphere and see if we can tease out some way to make this a little bit easier. By the way, I just answered this question for you. Does some of the forces in F equals ma in a Cartesian coordinate system make sense for us? I.e., is it easy? And the answer is no. And it's not, because everything is changing direction all of the time. So if we look at flow around a sphere, then we want to, even if we're just doing laminar flow around a sphere, that we have one streamline that's coming in dead ending because it hits it completely symmetrically on the sphere, so it just comes to a complete stop. And there's one that stopped and then accelerates away like that. And then basically all of our streamlines then will follow the sphere, becoming decreasingly, I'm getting lazy, but yeah, they'll follow the sphere around like this. Yeah. So again, the direction of the velocity changes all of the time, right? So if we look, this one's going in this direction, but then it's going up, sideways again, and then down, and that becomes a pain. However, one thing we could do is we could define a coordinate system that is always tangent to our streamlines. And we will call this coordinate system, we'll have two directions. We will have the velocity in the streamwise direction, and there'll be a velocity in the normal direction, right? So here's Vs for a straight line. Yeah, so now with this new coordinate system, we can look at the streamwise direction, which is always pointing the way that our velocity is pointing, and it will have a very consistent system to look at our some of our forces in. So we're going to use a blank coordinate system with a blank component and a blank component. So I've already said these words a couple times. Try to remember them. Pause the video and try to write these down. All right. Now if you couldn't remember them, we're going to use a streamwise coordinate system with a streamwise component. The streamwise just means in the same direction of a streamline. And a normal component. Normal component. Good. So, how does acceleration work in this coordinate system? Well, we can write that acceleration is equal to dv dt. That's what you're always familiar with, right? And further, we can use the, oh gosh, it's been like 2 decades now since I took calculus. I always forget this every year because I only say it like 2 or 3 times a year. Chain rule, I think. Correct me if I'm wrong in lecture. But we're going to use the chain rule to break this up to dv ds and ds dt, right? And now the important part is ds dt is our speed along our streamline per time. So this is just our velocity, right? So this is going to be equal to dv ds times velocity. Okay? So if we want to break this up now, we say a streamline, or acceleration streamwise, is equal to our velocity times our dv ds, and our acceleration normal to our streamline is equal to v squared over r, which should look very familiar, right? Where this is the radius of curvature, of the streamline. Great. So now that we've kind of set the scene, let's start our derivation with the most fundamental model of mechanical and aerospace engineering. And that is sum of our forces is equal to mass times acceleration. Yeah. So note we're going to do sum of our forces in the streamwise direction is equal to mass times acceleration in our streamwise direction. So that's going to be equal to rho dv. So that gets us our mass in our streamwise direction times our acceleration. And what are we going to do? We're going to draw another differential control volume on our streamline. So this is our streamline here. We've labeled it. And this is going to have a shape of ds in the streamwise direction and dn in the normal direction. And now let's write all of our forces on this object. Okay? So I'll do our gravity. Do mass times gravity. And we can actually break that down into 2 different components here. If we call this theta, we'll have a differential weight streamwise and a differential weight normal to the flow. All right. All right, so now we're going to do the same thing we did before. We have a differential element in a fluid flow. We know there has to be pressures on this object. So if we're summing all the forces, we have to multiply the pressures on each of the faces times the area. Okay? So I'm going to do one of these. Let's see which one I'll do first, and then I'll let you guys do the other ones. Remember, we've defined our pressure in the middle of our differential volume, or differential area in this case, because we're just worried about 2D flow, so it's just an area. And so I will do, I'll tell you what, I'll do this one. I'll do streamwise facing in this direction. And it is going to be equal to our pressure. It's always start with our pressure in the middle. And remember, our differential volume, we assume that the pressure changes linearly across our object, across our volume, because it's so small, right? It doesn't matter how fast it's changing, how curved it is. We've chosen a small enough volume that we can approximate it as a line. So we're going to say that our volume, or pressure on this end of our differential area is equal to the pressure in the middle plus the slope of our pressure, so dP ds, right, times the differential s divided by 2, because we're only going half the distance in this direction. And then again, we have to multiply that by the area. So we're going to assume we have some differential y into the page times a delta n, which is our normal width of this thing. Great. So that's that one. I'm going to have you guys do the rest of them. So pause it, write the rest of these. Remember, we're trying to do engaged learning here, which means doing the hard work, right? You can't just zone out and write everything that I write down and hope for it to stick in your head. We talked about this on the first lecture about how if you do this right, you can study for 60% less time. If you spend the time now in lecture, quote unquote, you can't tell I'm doing scare quotes, in lecture. Okay, so hopefully you paused and then fast forwarded through my little spiel there and you've written all these things down. Now I'm going to write them down. So on the top, we have pressure plus dP dN delta n over 2 times delta y delta s. And then on this side, we are going backwards, right? So we're going to have pressure again, always start with pressure, plus the slope, dP d s, and not plus this time, it's minus because we're going in the backwards direction. So we're subtracting dP ds times delta s over 2, and then multiplying that by delta y delta n. And then the bottom here, we have a pressure that is just P minus dP dN delta n over 2, and then multiplied by delta y delta s. Great. So we have all of our forces now, and this has been our free body diagram, because remember, every time you use some of the forces equal to mass and acceleration, you have to have a free body diagram. So this has been our free body diagram. So now we're going to do some of the forces. Oops, that's not the right color. We're going to do some of the forces in the streamwise direction. So let's start that. This is equal to P minus dP ds delta s over 2 times delta n delta y, minus, because this force up here is pointing in the minus direction, that's the one we're doing right now, minus pressure plus dP ds delta s over 2 dN dy. And then we're going to subtract our mass here. Our mass, our differential weight in the streamwise direction, which is rho g sine theta times our mass, which is rho times our volume. So we'll just say our differential volume for now. And this is all going to be equal to our rho times our differential volume. So differential volume times our velocity times dv ds. Good. So again, this is the beautiful part about using the differential volume. Some wonderful things cancel out. It doesn't matter what our base pressure is. It cancels out, but these two pressures end up adding to each other. So we get negative dp ds delta s delta n delta y minus rho g sine theta. Delta v is just delta s delta n delta y. That's that. Is equal to rho delta s delta v, delta n delta y times dv ds times v. Great. So now the most fun thing in all of engineering, at least until you actually do engineering, is canceling stuff out. So we cancel a bunch of stuff out, and we get that if we put everything on the same side, we get that put everything on the same side and then integrate it, we find out that 0 is equal to the integral of dp ds, and we're going to divide everything in here by the density. So we get 1 over the density, dp ds, plus integral of g. It turns out that sine theta is equal to dz ds, which is essentially the slope of our streamline at that moment. So sine theta is equal to that. And then plus the integral of v dv ds. Great. So, oh, you know what I did? I think I dropped 1/2 in there. Nope, I didn't. We're good. So now we can integrate this, but we have to make an important assumption before we integrate it, because integrating this 1 over rho and this g can become tricky unless we assume rho is equal to a constant and g is equal to a constant. Now we won't repeat this one because that seems pretty obvious. But we will assume that we have to assume that rho is equal to a constant. And if we do that, when we integrate this, we get that 0 is equal to pressure divided by the density plus 1/2 v squared plus g times z is equal to, sorry, it's not equal to 0. It's equal to a constant when we do the integration. Then that's our Bernoulli's equation. And there's a couple important caveats here, a couple assumptions we made. 1, density is equal to a constant. 2, we assumed that our integration was along a streamline, and that ends up being incredibly important. So in order to use that correctly, we have some rules for accurately using the Bernoulli's equation. Number 1, because we have to go along a streamline, if we're looking at turbulent flow, that becomes nearly impossible. So 1, we have to have steady flow. 2, no viscous forces. Oops, no viscous forces. If you look up here on our free body diagram, all we included was pressure and weight. If we had viscous forces, we would have shear stresses along these sides here, right? Acting in this direction on our body. And we will add those in eventually when we get to Navier-Stokes equation. But for now, we're ignoring viscous forces. So we have an inviscid fluid. And 3, whoops, get back to blue. 3, we need flow along a streamline. And 4, density is equal to a constant. So steady flow, first of all, I'm going to cut to the climax of this lecture here. And it's almost impossible to do all of these, right? So steady flow is not common, right? We often have rotating flows. In fact, most of our interesting flows are unsteady. So this is not common, but does exist. No viscous forces. Ugh. We're not working with liquid helium, so this is impossible, right? But remember that tau, our shear stress, is equal to mu times the gradient of our velocity in the direction perpendicular to the velocity direction. So if we're looking at the u component of velocity, it'll be in the y direction, for example. And remember that this is velocity and this is distance. So if we have, if we want to reduce the effect of our shear stresses, we can just have slow velocities and large distances, right? So, and that could help minimize the effect of viscous forces. And 3, effectively, flow along a streamline means non-rotational flow, which is very basically our steady flow assumption, but we're stating it again here just because it's so important. And the main reason this is important is because we can't add or remove energy or cross fluid boundaries, have fluid cross our streamline boundary. Finally, number 4 though is pretty easy. Water works pretty great. Gases, as long as your velocity is less than 0.3 times c, where this is the speed of sound. So in air, that's something like 250 miles an hour, something like that. So for the most part, unless you're flying airplanes or working with some pretty fast-flowing liquids, you can assume density is a constant. So what's remarkable about Bernoulli's equation is, in spite of all this, in spite of the fact that you can never accurately use it if, well, that's not true. You can never satisfy all of the assumptions perfectly. Bernoulli's is really quite useful. It's really quite useful. So, it's really quite useful in spite of these restrictions. So our next video is going to be an example where we're going to drain a pool because winter is coming to Buffalo. Anyway, we're going to drain a pool and calculate the amount of time it takes to drain the pool. And then we're going to work on our semester-long design problem too in the next lecture. Next video anyway. Cool. All right.